Now, in this lecture, we shall be primarily be discussing about the design of the members subjected to bending. So, when we are talking about the bending member, we do know that either we are talking about the beams or we can say we are talking about the girders. So, girders are like a term that is used when the span of the like member is like a very large. So, let us say if you're talking about the design of the plate girders that are used on the bridges, so in that we do say that okay, that is a girder. But if we're talking about a small building with let us say 6 meter span, or we can say 6 meter height or 5 meter height, so that if this member is like getting subjected to bending, so in that case it is known as the beam. So that is the difference in the terminology. Now, if we are talking about the design of the member subjected to bending as per AS 4100, so in that case, we primarily use the first of all the hot rolled I section that are easily available in the market. So they are like named as let us say UB610 or UB305. So we have already discussed what is the meaning of this, and the second term is the the weight also that is given. So UB305 into 37 means that the unit weight is approximately 37 kg per running meter of we can say 1 meter length of the girder. So if you want to talk about the the different types of members that are used for the bending. So first, as I said, the most common shape is the I shape member, and the member is the UB that is easily available in Australia. After that, the second type of member we can say that are used as let us say rectangular hollow section. So rectangular hollow section, the plus point is that the second moment of area about this axis is higher. So let us say if we want to make a 6 meter beam, so we ensure that this dimension is like along the we can say height of the section, so that whatever the we can say the bending moment are coming, we do have a strong we can say second moment of area along that axis itself. So that is the second commonly type used. Third commonly type used is the we can say whenever we want to support a gantry girder. So what we do is that we take an I section and we take a we can say C channel, or we can say parallel flange channel, and then fix it on the top of that. So that is also like commonly used in we can say industrial buildings. So whenever we have to support we can say gantry girder, that is usually supported on the track itself, and this track is basically fixed on to the top of this parallel flange channel, which is then fixed on the top of this we can say eye girder, and that is like commonly fixed from the this we can say column of the building itself. So that is these are the we can say commonly used bending members, and that are easily available in Australia also. So after that, we do need to understand the flexural member behavior, and it is not that the member that is uh, getting activated against the we can say bending forces. It only resists the bending moment. It also resists the shear also. It also resists the crushing also. Let me just explain it point by point. Let us say this is the ideal case of a bending member which is getting supported from both the sides. So let us say if we are putting the UDL on the top of it, so it we can say bend something like this, and this deflection is usually in the range of we can say 1 mm or 2 mm or 3 mm. I have just scaling it up so that you can understand. So this is the one example that okay, this is the bending behavior. After that, the second force, or we can say if we want to draw the bending moment diagram, so it is usually in something like this, and this value is usually WL square by 8 if we are talking about the UDL. The second behavior is that when it has to resist the shear force also because of this particular UDL itself, uniformly distributed load itself. So that shear force diagram is something like this. So we can say that this zone here, this zone is the one that is primarily resisting the shear force. And this zone here, that is primarily the one that is resisting the bending moment. So whenever the members are getting subjected to bending, we have to think about the bending moment itself. We have to think about the shear force itself. After that, the third behavior is that, at the point where it is getting supported. So let us say it is getting supported here and here. In that plate also, there may be a possibility of the crushing itself. We can say web crushing. That is a behavior that needs to be checked when, we are supporting the girder here. So if we want to draw a zoomed in view, let us say this is the I plate girder, and in here we are making a plate, and that is getting fixed on the, we can say, let us say, column. So this part here, this part of the girder itself, there is a very high possibility, because of the local concentration of forces, there may be web crushing. So what we usually do is that, in these kind of areas, so what we primarily do is that we do provide stiffeners here, and this end stiffener is many of the time it is required, especially in the case of the plate girders. So in the case where, we're talking about the hot roll section, that hot roll section usually have a capacity to resist the web crushing. But when we're talking about the very large plate girders with very thin webs, this web is usually in the range of 8 mm or 10 mm. So the shear force is huge in those areas. So in those cases, we have to ensure that we do provide some stiffeners here, so that we can disrupt the angle of the shear failure, which is usually, it is something like this, and we can prevent the possibility of the web crushing. So that is the, we can say, these are the cases. And additionally, there is a very, we can say, case which is a very less probability, that we can say the local plate buckling can also happen. So let us say those, that local plate buckling, local plate local plate buckling, that can happen either in the, we can say, flange, or that can happen in the web itself. So there may be a case where, the web itself can bend something like this, or the flange itself can bend something like this. So that also happens, when we're talking about the non-compact section or slender section itself. So in those cases, there may be a possibility where we are talking about very thin web, let us say 8 mm or 6 mm. So in those kind of thicknesses, there may be a case where the flange itself may locally buckle, or web itself can locally buckle. So that is the, like, basic introduction to the different kinds of, we can say, flexural member behavior. After that, the primarily, the thing that you do need to understand is the bending, we can say, bending moment capacity. So bending moment capacity, we have to go into the basics and understand that the bending moment capacity is equal to m into sigma into z. Z is nothing but second moment of area, and sigma is nothing but the yield stress, which is usually in the range of 250. So 250 multiplied with, we can say, the second moment of area, it gives us the bending moment capacity, which again needs to be multiplied with 0.9, that is 5 value here. So that gives us the allowable bending moment capacity. So sorry, we are not using the word allowable, because that gives us the philosophy of the allowable stress design. We say that it is the value of the bending moment capacity, and that we can name it as limiting bending moment capacity also. But before that, you do need to understand that it is not that, as we have discussed in the column design also. Let us say we're talking about the beam. So let us say we do have a beam here, and that beam, we have two beams, the same beam UB305 into 37. Again, we have a second beam UB305 into 37. But the only difference is that we do have, let us say, a metal deck sheet on the top of this, and we do have shear studs And this beam is standalone single. Let us say this span is approximately 6 meters. This span is also approximately 6 meters. There's no as such, restraint on the top of this beam. Here we have no restraint. We have full restraint in this particular case. So, if I'm asking this question that in which case the bending moment capacity shall be higher. So this is the case where the bending moment capacity we can say that shall be higher, and in this case the bending moment capacity shall be lower. Why? Because when we're talking about the bending moment capacity, we are talking about the restraining conditions. So restraints are the one that governs the bending moment capacity of the steel beam. In this case, we do have full restraint on the top flange. So we can simply use m equal to sigma into z in this particular case. But in the case where we have no restraint, we do have to consider it as unsupported, laterally unsupported beam, in which we do have different calculation, and with that we shall be discussing in detail in the next lecture. But the first fundamental that you do need to understand is the steel beams with the full restraint condition. So in that case, in majority of the cases, either it is provided with the help of the metal deck sheet, or it is provided with the help of the we can say plan bracing, or it is provided with the help of we can say some kind of sheeting system on the top, obviously solid metal sheet on the top. So in those kind of cases, we can proceed with the full restraint condition. But we can say if there are no as such restraint along the length of the beam, then we have to proceed with the no restraint, and the formulae are different. This formula is not applicable, that is m equal to sigma z, that is not applicable for beams with no restraint, or we can say partial restraint also. So to first understand the concept, we shall be discussing about the beams with the full restraint. Let us just discuss m equal to sigma z here. First of all, if the concept is clear to you, then we shall be discussing with the beams with the partial or no restraint, for which we do have different formulas. So now we shall be discussing about how we can do the practical designing of structural steel beam when we are talking about what we can say the beam which is laterally supported at the top flange. So the calculation for that beam is very simple. As I have explained that we can just simply do the m equal to sigma z, this particular formula, that is the bending moment capacity is nothing but the yield stress allowed multiplied with we can say section modulus, or in some conditions second moment of area. So what we can do is that we can just open the ETAP software and we can select metric SA Australia and all of these parameter AIS 4100 2020. So we can select these values as 2 and 2, and number of stories as 1, 3 story height, that is okay. And after that we can go to the we can say define. We can go to the define and material properties. In here we can see that ES 3679.1 300 and thickness is between 11 to 17 mm, so that is okay. And after that we can go to the define and section properties and frame sections. In here we do need to select the import new properties, and from here we can go to I wide flange section. So here we are talking about the thickness between 11 and 17 mm. So what we can do is that we can select, let us say UB 610 and 101. So we can left click on OK, and after that we can go to the modify and show property. So in here we do need to again check the thickness of this particular structural steel beam. So the thickness of the flange is 14 mm and the thickness of the web is approximately 10.6, or we can say 11 mm itself. So this is fulfilling the criteria of this particular structural steel beam. And if we go to the show section properties, in here we can see that the Z33 value is approximately 2900 centimeter cube. So what we need to do is that we do need to enter 2900 here, and sigma is basically 300. Let me just show you the material property also. So if we go to this particular option here and we go to the modify show material, in here we can see that the grade of the structural steel is 300. So if we left click on modify show material property design data, here you can see that yield stress is 300 MPa. So it is a very simple math here, and what we need to do is that we do need to multiply 300 that is the yield stress, multiplied with the 2900, that is the Z33 value, multiplied with 1000 because 2900 was in centimeter cube, and that needs to be divided with 10 to the power 6 for the answer in kilonewton meter. So 870 is the kilonewton meter, which needs to be multiplied with 5. That is the bending strength reduction factor for bending. So the bending moment capacity, as per the software, it should be 783 kilonewton meter. Now let us just model the software and check that whether the calculation we have done is correct or not. So we can go to the draw and beam, column and brace. So what we can do is that we can select here as simply where we can say pinned and property as UB610101. So we can just simply model this particular structural steel beam. We can go to this particular select object window. We can go to the 3D, and what we can do is that we can select all the nodes here and assign joint and restraints. So we can select fixed node here, apply and OK. And additionally, we can press Ctrl W option on a keyboard, and under the section of this object assignment, we can open this particular end releases option also. So here we can see that this beam is simply supported with fixed conditions at the ends. This is just to stimulate the, we can say, simply supported behavior of this particular steel beam. So we can go to the assign frame loads and uniform distributed, sorry. So under this option, we can select, let us say 10 kN per meter UDL on this particular steel beam, and direction can be gravity. So we can apply and close. So after that, we can go to the analyze and set load cases to run. We can just switch off the model case because we really don't need that. And live load, we have also not applied any kinds of live load, so we can also switch off that. And then we can just left click on run now. So here we can see that the ETABS has analyzed this particular steel beam. So what we can do is that the only thing missing is that we have not stimulated the laterally, we can say that the top flange is laterally braced, because the calculation that we have done is for the laterally supported, fully laterally supported beam. So we can go to this particular option again, and we can go to this particular lateral bracing option, and we can click on user specified, specify uniform bracing, and then just left click on add. It signifies that the whole length of this particular steel beam from 0 to 1, that is basically the we can say function. So if it is 8 meter, then 1 into 8. If it is 9 meter, then 1 into 9. Or in some cases, if you want only half of the beam is laterally supported, then you can enter 0.5 here also. So we can left click on OK, and then again left click on OK. So after that, we can just check this particular view revise preference option. In here, we can see that it is AS4100 2020, and our phi bending is 0.9. So that is okay. And after that, we can just click on this particular option, that is steel frame design. So we can left click on this particular steel beam, and then again right click here. So in here, we can just go to the overrides option here. Under the override option, in here you shall see that major bending moment capacity that has been calculated is 783 kilonewton meter, and that is the same value that we have calculated in our manual calculation. So it is as simple as that, as I was explaining to you like few minutes back, that m equal to sigma z, that is applicable when we are talking about the, we can say the fully laterally supported beam. And you don't need fancy softwares to do that calculation. If it is a very simple case, you can just simply open the manual here. So let us say this is 610 UB, and this is for the grade 300. So in here you can just simply find out the ZEX value. In here it is 2900. Just multiply it with the grade, and we can say divide it with the we can say or multiply it again with the phi. That is the bending reduction factor, to find out the maximum bending moment capacity that is allowed. So I hope this concept is clear to you. And similarly, major shear capacity and minor shear capacity, that also I shall teach you, and it is very simple calculation. And compression, that we have already discussed in our earlier lecture, considering it as a, we can say, compression we can say strut member, that also we can calculate. And in the next lectures, we shall be discussing in great detail about the KT, KL, and KR factor. These factors are very important, and it is important that we do need to understand that in context of AS4100 code itself. That is what the code is saying, how the software is calculating, and how we can practically check all the we can say values. Now in this lecture, we shall learn that how we can do the same analysis as per the NZS3404 also. So principally the concepts are same, everything is same. So what we need to do in the ETABS is that we do need to go to the design, steel frame design. And in here, we do need to select under the view device preference as NZS3404. So we can find the NZS as here. So all the options are same, everything is same. The capacity reduction 5 for bending, that is also 0.9. And we can left click on OK. And then after that, we can just click on the steel frame design option again. Yeah, but before that, we do need to do the analysis also, because we have save as the model this particular part. So now we can select on this particular option as steel frame design. So we can again left click and then right click again to see that what exactly is the bending moment capacity. So in here we can see that that is again same, that is 783 kN as we have checked yesterday. So we can left click on details also. So here you can see that the code is showing as NZS3404-1997. The capacity moment reduction for bending, that is also 0.9 again. And after that, we can again see the different parameters. So in here it is checked that whether the section is slender or non-slender. So here you can see that all the components are non-slender, and all the like parameters, because ultimately the software do check the axial force and bending moment also on that, both major, minor, shear, and torsion. That is like the algorithm of the ETAP software. So ultimately it is checked, but overall you can see that here axial force itself is 0. So overall it has a capacity of, we can say, this 3214.836 kN multiplied with the, we can say, capacity reduction factor. But it shall ultimately show the result only for the bending only. So against the bending of, we can say, 118 kN, it we can say it has capacity of 870 into 0.9, that is 783 kN that we have checked. So the principle is same, everything is same. So there is no as such, we can say, major difference between the design of, we can say, structural steel beams as per AS4100 or NZS3404, that is New Zealand standard for structural steel sections.